Okay.
Okay, so this is the last, I think it's the last talk of the seminars from the Quantum Computing Mastery from the Universidad Politécnica de Madrid. Today we have with us Santiago Murillo. Santiago is an industrial engineer and he's also a researcher in computer science. He has more than 15 years of experience in technology innovation, artificial intelligence, and advanced analytics. He has been working in the Spanish financial services entity CaixaBank from 2017, I think, and he's working within the innovation department. He leads projects and assesses how quantum computing can be applied in the financial services industry. So thank you again, Santiago, for joining us and sharing your experience with us. It's great to have you here. So over to you. Thanks.
Okay, thank you very much for having me. Well, as Rafa said, I work in innovation department. We work in different tracks for financial service with the up-to-date technology. The main tracks that we work in now is blockchain, especially for trade finance, digital identity, and tokenization. We have a very big track in advanced artificial intelligence and fintechs in order to introduce new technologies to improve the service of the bank and also to create new service and products in banking industry. And today we will focus on quantum and especially our experience in quantum simulation and optimization development that we have performed in the last years. So regarding quantum computing, I'm sure you have seen this in the seminar this week, but just to remember that it's a very live field of investment in around the world. So for 2021, we have 24 billion estimating investment is only in public funding. So we see a very like a growing trends in investment in quantum, also in private and public sectors. And this is an indicator that the industry will introduce, will change the reality that as we know today in advanced analytics and in financial analysis. Quantum computing is not, well, the real quantum computers are not there yet, but we need to be quantum ready. So the many sectors are working in post-quantum crypto, and financial sector is a very, very important field to research now. Also in optimization and simulation and machine learning. All the banks, well, the main banks, and also the industry as telecommunication or traveling or, well, security are working in development application to provide solution that is not feasible in classical computers, especially in bank. There is a lot of application for simulation because there's a very high resources computing consuming when we try to simulate some scenarios. And also there is a upskilling track in some banks. So there is a lot of banks that have like a quantum expert groups that they work with, especially, for example, in Morgan or BBVA have a very important group of researchers in quantum. And also they have a link with the universities as the Polytechnic of Madrid or Polytechnica of Catalonia or around the world. So there is like a growing research field of quantum computing in this communication between industry and universities. So the quantum advantage, some experts say there is not yet. So, but there will be in the next 10 years. So in the next 10 years, we need to be quantum ready when this quantum advantage happen. And meanwhile, there exists the NISQ hardware. The NISQ hardware, as maybe you know, this is the noisy intermediate scale quantum. That means there are some machines that we can use today, and we have like no quantum advantage, but see a quantum application that perform better than the actual solutions. So in financial sector, quantum computing is taking off. So we have a lot of news in the newspaper regarding quantum application, especially for my company, CaixaBank, where I work. We have developed some use cases in the POC frameworks, but also there is now beginning to appear like commercial application of quantum computing. So Goldman Sachs is one of the leading financial institution applying quantum computing, but also JP Morgan or BNP Paribas. So there is like a trend to improve and to invest in quantum development in financial sector. So sorry. There is some examples of how to apply quantum application in finance. Barclays, for instance, has an application of transaction settlement optimization. This problem is very hard to compute because there has a lot of restriction and features to proceed. They take like 200 CPUs and a large amount of money and memory to process. So there is a example, the mixed binary optimization that they test in IBM Q network, and they have a publication for that. Also, there is an example of JP Morgan. They are investing a lot in, for example, derivative pricing analysis. We will see in our examples why this is important. And also they are investing in protect or improve the cryptography of the assets. So they have a research field into Fibonacci series estimation in order to improve the cryptographic capabilities that they have. They use another provider, Honeywell, which they use trapped ions hardware. So it's a different approach of IBM, a different approach of IonQ, for instance. Also in the Spanish market, we have BBVA. They have several papers published. One of them is the static asset optimization. They use that with more than 100 assets, but they use the Fujitsu digital annealer. Well, there is a discussion whether Fujitsu is a quantum or not, but it is an annealer simulation. So we have a quantum-inspired solution for a real problem. Also, there is a dynamic asset optimization. This is like a next level of difficulty of this problem. So they use the wave and they compare the wave with IBM. And also they have some projects going on with derivative pricing optimization. When we talk about derivative, we talk about hedging. What is one of our use cases, the last use case of optimization. And this is a very important market in derivatives and hedging. We are talking about $1 billion of investment. And if we can improve the performance of the algorithm in 1% or 0.1%, we will have a very high impact. So if we focus in the main use cases, that is derivative or risk analysis, or well, the 5 most use cases that you can find in the literature, they are based in the Monte Carlo simulation. So in finance sector, we always simulate the scenarios based in a probability distribution. So we take like thousands of scenarios, and in order to simulate these scenarios, we take days to, for example, for our assets of 1 million, we take 7 days running this simulation. With a quantum computer, we can run this simulation theoretically in terms of hours. So we pass from 7 days to 8 hours. What that does mean that we can produce faster solutions for the same problem, but also we can analyze a lot of more scenarios that we analyze today. So the propose for the in quantum world of the Monte Carlo simulation is the amplitude estimation. Maybe you have some of you have read the paper, but this is an algorithm that has been proposed in the 90s, and now it is improved, and it is a reality that we can run this algorithm in the actual hardware. There is an implementation of IBM. It is open source. You can download the library and test it in Qiskit. But what does amplitude estimation? Amplitude estimation is amplify the possibility to find a solution. And because you have a higher probability to have the correct solution of a simulation, you can reduce the time of the simulation. So since the amplitude estimation is in the file of portfolio optimization or risk analysis, the real problem can be simulated in the IBM Qiskit simulators. So there is another problem regarding when you are analyzing the derivatives or try to estimate the value at risk, which is the main metric that we want to find in this scenario, which is the estimation of the Gaussian distribution of the asset. So each of these scenarios has a probability of happening. So we need to estimate the accumulated distribution of probability of these scenarios. But the quantum computers are really small now, so we need to code the distribution of Gaussian, which has a lot of chunks, but we need to reduce that in this case for 4 chunks. So we need to reduce the complexity of the problem in order to estimate and to simulate this problem in the actual resources that we have in IBM or other providers. So the two key message of this example of how you can use quantum computing to produce a Monte Carlo simulation is first, have a technique to reduce the complexity of the problem, introduce that in a simplified way of the Gaussian multivariate distribution. So in our case, we reduce the Gaussian chunks to 4, which is low. So and after that, we use the amplitude estimation. The whole circuit of the Monte Carlo simulation is this one. So it's like first we have to upload the Gaussian distribution simplified of the assets. So each you estimate the probability distribution for your set of assets. You upload that into the circuit, and after you estimate the probability of default of these assets. So when you make this Monte Carlo simulation, you are trying to find what is the probability of the assets of the default of the assets, in order to have like the capital that you need to cover this risk. So it's like you estimate how much money you can lost in your investment, and you need this capital in order to cover this risk. So that's why we call that the value at risk, is how much of your investment are in risk or default. So we run that several times in order to get the final solution, and the the good things of the amplitude estimation is that it reduces the number of times that you need to run the algorithm in order to find the solution. So in our use case, we use a toy model of 2 assets. It's a toy model because we have normally million of assets, but we need to test the technology. We need to test that we do it with a quantum computer. We will get the same solution that we get in a classical one with the same amount of assets. With this is 2 assets. So the solution converges in only 5 iterations. So after 5 times we run the circuit, we get the solution that we were looking for. And if we extrapolate this time at this segment of the problem, we estimate that they will run the analysis for 1 million assets in 8 hours. So this is like too good to be true, but we hope that some days in the next years, we will find the quantum computer big enough in order to test this algorithm with a higher number of assets. Okay, but we have another approach to accelerate the Monte Carlo simulation. And I insist in the importance of Monte Carlo simulation because it's the base of risk analysis and portfolio optimization and derivative optimization also. And also for hedging, which I say is a very high volume market. So we are trying to find how to accelerate this Monte Carlo simulation. And there is a proposal to use quantum random number generation. We use that with a QCT, which is a startup located in Barcelona. And it's a spin-off of ICFO, which is a high-level quantum institution in Spain, specialized in quantum photonics. So they produce entropy as a service, and they produce random numbers based on photonic. So if we have the process of simulation, when you generate a random number based in a classical hardware, you have the calibration, the simulation, validation, and sensitivity. If we are sure that the quantum number are physical random, so we don't need the phase of validation. So we have a shorter period of time to generate these quantum random numbers to use that in the Monte Carlo simulation, because we need to produce different scenarios with this entropy. So if we externalize the producing of the quantum number, we can free some computation resources, and these computation resources can be used in the probability estimation and the value at risk estimation. So the hypothesis here is if we use the quantum number generation, you can accelerate the Monte Carlo simulation by tenfolds. And we test that with a real set of assets, and we find that using the quantum number generation in external framework using QCT entropy as a service, we get acceleration even in 12x for different kind of models. These kind of models are the different ways to perform the Monte Carlo simulation. So we have the equity models, which is a piecewise Heston, the two-factor models, or correlated models. It doesn't important which models do you use, we get this acceleration. But the acceleration increase when you increase the use of this entropy with this randomness. So it will create, it will increase the benefit will be increased more if you have more assets, if you use more intensively the entropy in your analytic pipeline. The accuracy was good in our testing, so we can be sure that if we use this photonic random generation, we can get an acceleration of the quantum of the Monte Carlo simulation. And also they have another benefit, which is to have a better distribution of the solution. And it will lead in a less variability in the estimation. So we will have less error in the estimation. We decrease the number of simulation in order to have a final solution. So we can perform 5 times more simulations. And when you are in the analysis of the risk assets, you need to be very fast because you need to take decisions on which assets you need to buy. These kind of assets are bonds or stock options or put options or different financial assets. So if they can change the value even in hours. So if you can speed up the analysis that you made over these assets using this quantum technology, so you have like a window of opportunity in your investment. So finally, you can have like a very high impact in your revenue. So another use case that we are working now in is the quadratic optimization. So where you have quadratic optimization in financial world, you can accelerate the trade settlement capability because there is the quadratic optimization is a methodology that is very good when you have a very high dimensionality or when you have a lot of parameters in order to compute your final solution. So the settlement capability, when you have financial settlement transaction, you have a lot of features and you have a lot of dimensionality. And quantum computing can process a lot of states at the same time, so you can have a very fast optimal solution. Also, when you monitor transaction and when you rebalance the products that you can offer to your client, and you can align this product according with the risk profile of the client and also with the objectives or revenue of the client. So you can improve the decision that you make in order to have a better service for your clients. And also, if you have better service, you improve the retention of the customer, and also you can have some better analysis of the churn and predict the churn. So when the use case where CaixaBank is working now is in the portfolio management optimization, which is a problem of asset selection. And just to explain you what is this problem. So you have a set of assets. Each of these points are an asset. And this curve is the expected volatility, which is the risk that the asset has. And also the expected return, which is the return that you have in an investment. You know that with higher risk, you have higher return, but you risk to lose your investment. So there is like a frontier of safety that the bank has to respect in order to, because regulatory reasons, because we need to keep the money of the client safe. So we need to choose the combination of assets of these possibilities in order to maximize the return of the investments, but with some constrictions. These constrictions are the risk of also the time also the volume of the investment. So we have a lot of parameters in order to take in account when we select the set of assets that we buy for a specific client. This is a hard problem. So we need to, the solution that we have now is a heuristic that we say the best solution that we can have with linear programming. So if you have in mind some simplex method or this kind of linear programming that we used to. So quantum computers bring with the capacity of have a solution of quadratic problems. This is a higher dimensionality of the problem, and to have a global optimum of the solution. And especially the solution is quantum annealing. And there is a main provider, Derivates. They are from Canada, and they're working in annealing. The quantum computer of Derivates is based in the tunneling, the quantum tunneling. That means that they can reduce the amount of energy in a adiabatic computation, so we get the global optimal of the solution. So you upload the definition of the problem in these equations, and the system run the adiabatic decrease of energy, and you get the global solution. We have tested in different use cases in portfolio optimization and hedge. We are having a very good results now. We will publish that in the next weeks, but it is a real problem solution. That means that we can apply now to the set of assets that we have now in the market. So the message here is we can use now quantum solution, in this case, the wave in annealing approach, for solution of the real problems that we have now in asset allocation. And also there is an approach to machine learning. Machine learning has like different parts where you can apply an optimization. So you can apply an optimization in future selection. You have applied optimization in find the specific kernel, and also the optimization to have the best model. So you can split the problem when you are training a model in artificial intelligence. You can have a hybrid approach in order to solve this problem. There is an important proposal for the scientific community, which is the quantum enhanced future space, which is a transformation of the futures into the quantum space. The effect of this transformation of the future space is to increase the dimensionality of the future space, and you can find like in a linear way a solution of the problem which is not linear, as you see in the diagram here. So you have a two-dimensional points, and you apply the future space. So you have a increase in dimensionality, and with an hyperplane, you can find the hyperplane that split the two set of futures. So if we think in a risk analysis, when you have to split the good clients with the bad clients, let's say the people with a high risk and level risk. So this is very useful when you can take decision of which person you will give a credit. So we implement that in a quantum version of a support vector machine. That means to have this to find the plane that is the split our clients in a good clients and bad clients. We need to simplify the problem because the number of qubits that the quantum computers have available now are not enough to proceed a high data set or a high dimensional data set. So we reduce the data set to 10 futures, and I think was 1,000 clients. And we test to find the best model of risk scoring, and we will succeed. This is the quantum circuit that we implement. The first one, the first gates are the variational, and after we have the quantum future mapping. Okay, so at the final of the circuit, we have the best kernel that define this hyperplane. So this is the circuit that we implement. So we have the future map, the variational map, but we implement that in a hybrid weight. So the optimization of the theta, which is the parameters, we run that in a CPU. So we find the parameters of the variational in the quantum circuit, and after we proceed the optimization in the CPU. We have very funny, curious findings here. Is when we increase the number of qubits that we use for each filter, we don't have a better accuracy. So it was counterintuitive because all of us think that if we have more qubits, we have better solution, but it's not the case. And there is a phenomenal web documented in IBM, which is the Barren Plateau, and it is linked with the kind of qubits that they have, and also with the quantum error correction. So this is also an important message for you guys: is more qubits is not enough. You need a more stable with less quantum error qubits that you can. So in this case, having more qubits was worse. We get a worse precision. And I think we can be sure that in the next years, they will have better hardware, and they will correct also with software or with better hardware. And we can implement like a very huge problem in the next years. And just to finish and to open for the question, we have the challenge ahead. So the challenge ahead are as I say, the quantum error correction, and IBM referred to that as the quantum volume. That's meant to have like a more larger time of quantum currents, and also some correction through software. Also have the quantum hardware scalability in terms of number of qubits. And also, I'm sure you are aware
Santiago, can you hear me? I think he has lost the connection. Yeah, same. I wasn't sure whether it was me or the overall meeting. We'll leave a few minutes just to try and connect with Santiago again. In the meantime, please remember, if you have any questions, you you can try to drop them in the chat. I'll see if I can contact Santiago in some way.
Hi.
Hi, Santiago.
I'm sorry, I lost the connection.
It's fine, don't worry. I think we have seen the slides from before. I think the system got stuck with the two connections. Let's see if we can fix it. I'm giving you permissions again, and maybe I can remove the previous session. Okay, I think it's working now. So you're sharing your screen, right?
Okay. Yeah, you see the last slide?
Yeah, I think it's working now.
Okay, so but I just finishing. So the challenge is the research in quantum algorithms and developments, and this is the challenge where CaixaBank are focusing now, because it's not quite easy to have the quantum implementation of the current problems. So we use the open source proposal, and we work very close with IBM and also Stefan Werner, which is like a key researcher, and also with some important institution in Spain, um, where they have a very high profile researchers. And there is a few. I'm very happy that you have your master, because there are very few people that know how to code in quantum and how to bring real examples of quantum computing to the industry. So I also want to say that there is a lot of options now to implement quantum computing. There is a lot of options of simulators, and for example, Amazon and Microsoft will open their framework for different kind of hardwares, so you can test a lot of implementation and options. And also IBM has the examples in Qiskit, and they are open source, and you can test in real quantum hardware. So there is a lot of options. So you need only to have like the desire of learning.
I think it was on mute, sorry. Absolutely, and I think it's a great timing to start getting prepared for this technology and to start exploring the different applications. I think we lost the slides, but it's fine because I think we were finishing at this point. So now we are going to open a Q&A session. So if any one of you wants to ask anything, please feel free to just mute yourself and ask directly, or you can just drop them in the chat and we will try to address your questions. Thank you, Santiago. In the meantime, I had one question of my own. It was just out of curiosity. So in one of the slides at the beginning, when you were talking about I think it was the portfolio optimization, you were mentioning that once we have this quantum computer that is available and ready to execute these algorithms, you were estimating that it will require around 8 hours of processing to try to deliver results with a real data set. Are you getting estimations also on the hardware requirements for that scenario, like number of qubits or error rates in some sense?
Yeah, for 1,000 assets, you will need 100,000 qubits. So this is the magnitude. So this is with the actual landscape, but the things are changing a lot. The algorithms that exist is improving. So maybe you will need less number of qubits, or the qubits will change. So you will need less because the qubits by itself will be different. So by now we will need like hundreds of thousands of qubits in order to proceed a real Monte Carlo simulation for the assets that the final industry use. But having said that, there is a lot of use cases that are not as complex as that. So maybe in 3 years, when you have thousands of qubits available, you can run a real life problem.
That would be very exciting. Absolutely. Okay, we have a question from Felipe. Is it possible in the future to predict the changes in cryptocurrencies with quantum computing?
Well, changes is the thing that we do with quantum simulation, because we predict the change in the price of an asset, and a cryptocurrency is an asset. So it's like a stock or whatever. It changes value over the time. So the answer is yes, it will be possible, but you will need a very good quantum computer.
Absolutely. It would be quite challenging, but in the end, they are just financial assets. Okay, thank you from Felipe. Okay, let's see if we have anything else. That is great that financial service entities are already exploring this and trying to assess the timings and the roadmaps and building the capabilities for the teams within the entities. So that's amazing.
Yeah.
Okay, I don't see any more questions for now, but in any case, if anyone, please. If anyone wants to reach out at any point, we can always try to answer anything else that comes up, or maybe forward your questions to Santiago and their team. We have another one from JD. How much quantum advantage has been achieved in the financial services domain that we can use practically now? So what is closer, I think, is the question.
Yeah, the closer to production are the optimization approach using annealing. This is, well, is the after made a lot of testing and algorithm and POCs and whatever. So we see that the approach of annealing is close to production, but it is just for quadratic optimization problem, not for all kind of problem. So it is very narrow field of application, but it's very useful. So if we can optimize the asset selection, which is a very important problem in finance industry, there will be a quantum, I will not say quantum advantage, but well, there is a better solution that the classical computers have. Also, there is a proof that there is a better solution for travel optimization, like the seller traveler problem, and the D-Wave system had find a better solution that the classical computer has, and also for logistic distribution, there will be in the next year or next 2 years quantum advantage in that field.
That's exciting.
Thank you. I have a different question. So how difficult, because in our classical data set maximum, maybe in the finance or pharma, this is a very sparse. I mean, you have lots of null values, or it's not very much curated. So if we try to use those data sets in our current quantum realm, how much do you think it will be useful? Or we need again all those data clear? I mean, you have to clear the data and everything, then we need a final good data only to feed into the quantum system.
Well, the problem about the data loading data is well, it's a file of researcher because we don't have like a quantum RAM memory to store the big data sets that we need to run big programs. So as soon as we have this quantum RAM, it will be easier. But in our POCs, which is like, as I said, a simplified version of the problems that we have, we spend a lot of time in data processing, because you need to discretize all the values. You need to simplify the probability distribution. So you need to have a lot of data processing in order to use quantum computing as they are today. So this is in the general quantum computer. This is the gates quantum computers. But in the annealing version, there are more close to use the data as we use today in the analytic pipelines. So depend of the architecture that you're using, you can have a frictionless experience now. I don't know if I understand, if I answer the question.
I mean, my main question, it is perfectly okay. Yeah, I completely understand. And I could see in quantum realm, we have a lot of the inbuilt errors that we are dealing with right now. What I'm trying to see is basically, I mean, if we divide this machine learning into basically the two parts. One is the data curation, data engineering. Second part is basically model.fit and model.predict. So that is a two line of code for fitting and predicting. But main our effort is on the error correction within the data and all this. So how do you see this current classical data set and all the errors with that data set? First, if we use in quantum, how we can get the quantum advantage of fixing those?
Yeah, we split the problem from the machine learning just to estimate the kernel. So we use in this framework, we use IBM and also Xanadu. And why I say that, because it is better if you have in the same system the classical and the quantum part of the process that you will process. So the Xanadu, which is provided from Canada, they have this option to have the hybrid approach to proceed the full process. And in IBM, you have to split the process, and you have a lot of error, as you said, when you send data to the different processors. So there is also a trend now, which is the quantum-inspired solution. That means that you have a variational that you use in the quantum processing, and you estimate the last layers of the training in a neural network with this variational. So it's similar to the transfer learning, but you use like a approach that you use in quantum computer for the classical training of a neural network, of a machine learning model. So you don't need a quantum machine now, but you can use the quantum approach to the quantum neural network training in a classical computer. You can get a smaller version of your model because you reduce the size of the final layers of the model in the neural network. So you have different approach. You can have IBM in a hybrid approach and have this training, the splitting the process, but you have a lot of error because in the transmission of the data, you can have this kind of errors. You have Xanadu approach with the penny lane have all that you need to train in a hybrid way, and you have less error, and you have like a conversion of the solution. And also you have the other approach now that you can use now, which is the quantum inspired methodologies.
Thank you.
Okay.
Okay. I don't know if there are any other questions from anyone in the audience. Okay, I think we can close the session. And if any of you have any other questions, feel free to reach out, and we will try to address them. So again, thank you very much, Santiago, for sharing your experience with us. It was a great talk, and we hope to see you again in the future. So thank you, and thank you everyone else for joining us.
Sure. Thank you very much. Enjoy the weekend.
Have a nice day. Bye, everyone.
Okay, goodbye. Bye.